It's my pleasure to invite Pascal Koiran to give this talk today. Pascal, in fact, has been, like Nina, one of the two people who attended almost all talks in the GCT, I think. In this
a lot
series.
of them, not quite all of them, but yeah, a lot of them.
But most of them, yes. Mina has attended almost everything but one, I think. Yeah. So Pascal will be talking about tensor rank and commuting matrices.
All right. Yes. So today I will talk about a very simple model of arithmetic circuits, namely sums of powers of linear forms. And we have seen that previously in this conference. Just to remind you, the model looks like this. So we have some multivariate polynomial f, and we want to express it as a sum of df powers of linear forms. Okay, so of course, f is of degree d. And the smallest possible r here is often called the Waring rank of f. We saw that terminology already, I think, in Nitin Saxena's talk a couple of days ago. Can you hear me all right, by the way?
Yes.
Okay, great. All right, so for this model, we have nice lower bound when the number of variables and the degree are allowed to go to infinity together. In fact, we have exponential lower bounds. Obtained by the method of partial derivatives. So this goes back to, I guess, 1995 or so. And that's the work of Nissan and Vigdorsen. And this was covered already, I think, in Ramprasad Saptarishi's lectures on lower bound methods earlier in this semester. So this is all fine, but for small degree, the current results that we have are not so satisfactory. Even for degree 3, so this is the case I'll consider today. And degree 3 is relevant, for instance, if you want to talk about the complexity of matrix multiplication, but I'm not going to focus on matrix multiplication in particular in that talk. Okay, so for degree 3, what would we like to have? Ideally, we would like to have n square omega of n square lower bounds for some explicit polynomial. And it's known that this is actually the worst case. So any polynomial of degree 3 in n variables, you can write it using order of n square terms here. So if you can do this, this is as good as possible, at least up to the constant. And unfortunately, the current lower bounds are only of order n. They're on order n, and in fact, there are some barrier results showing that you cannot go beyond that using the so-called rank methods. So I'm not going to define exactly here what a rank method is, but let me just say that the method of partial derivatives or most other lower bound methods in algebraic complexity are rank methods. And so this result is due to I think Efremenko, Garg, Oliveira, and Vigderson. And there is also a follow-up work by Vizu Makam and some co-authors, and so actually they actually give some explicit value for the constant. You cannot do better than maybe 6n or 8n or some small constant times n with the rank method. Okay. So we to make progress we need non-rank methods. We need something else. So you can try to invent something from scratch, but turns out that there is at least one old non-rank method that is known from the literature, and it's due to Strassen. What I would like to do today is to see how we can put this method in a broader framework to try and generalize it, and I will focus here, in fact, on the case where we have real polynomials. So the LIs and of course f are going to be real polynomials, and it's a setting which actually has this real setting has some present features compared to, say, the setting of complex numbers, and I'll try to explain why. And to approach this problem, we are going to view it as a tensor decomposition problem. So let me first explain how you view this as a tensor problem. So by the way, I gave a presentation a few months ago at a workshop on a related material, but it was focused on ordinary tensor decomposition and the field of complex numbers. So if you by chance you saw that talk, you may still learn something today. Today we're going to focus on, as I said, on the real numbers, and since the model is the sum of powers, we are going to deal with symmetric tensors. So let me try to explain what those are. So what is the tensor point of view? What is the tensor point of view for this problem? So basically, when you're given this degree-free polynomial, now f has degree-free. The tensor, the relevant tensor, is just the array. It's the array of coefficients of f. Okay, so this is the tensor T is just basically this three-dimensional array. Okay, it's n by n by n array, and it is a symmetric tensor. Meaning that the entries are invariant under all the permutations of the indices. So for instance, Tgik is equal to Tijk is equal to Tikj, and so on. The 6 permutations leave the entries invariant. So that's what a symmetric tensor is. So remember, we had this decomposition as a sum of powers. Now, if we write it as in a tensor notation, we have, as I said, a symmetric tensor decomposition. Okay, so we're going to write T as a sum of R tensorial cubes. Okay, where UI now is a vector. And in fact, so the UI is basically just the vector of coefficients of a linear form here, right? So the linear form is just the inner product of UI and X. Okay. So so one reason why actually this tensor point of view is useful is that you can start using methods of linear and multilinear algebra. So in this talk, I'll just do some linear algebra, and one way to do this is to cut the tensor into slices, right? So you fix any of the 3 indices, and you get a matrix. So you have n slices. So for instance, if I look at the kth slice, of T, it is the matrix with entries defined like this. So the entry ij of k is naturally the corresponding entry of T. It's Tijk, okay. And now, since my tensor is symmetric and real, this is a real symmetric matrix. And as you all know, real symmetric matrices have nice properties. So that's the reason why working here over the field of real numbers is nice. All right, so that was my introduction to this tensor point of view. And then let me now try to present the proposed approach to get some lower bounds from this point of view. So the proposed approach is, you could call this the method of commuting extensions. And as I said, it really goes back to Strassen, but he didn't use that word. I'll show you in a minute where this terminology comes from. Okay. So when I mean commuting extensions, so actually it starts really with extensions of matrices. So so I'll take a small detour through a problem purely about matrices. So it might not be obvious at first sight what is the connection with tensor decomposition, but hopefully it will become clear a bit later. So let's talk about this matrix problem. So what is this about? Well, we are given some square matrices. We want to extend them in order to obtain commuting matrices. So what do I mean by extend? It's really extended by adding rows and columns. So really, so I have my data A1, AK. Okay, and we want to extend them, construct a bigger matrix. So the AIs are going to sit in the top left corner here. Okay. So you construct a bigger matrix Xi. So AI is going to be of size n by n. And you want to construct a bigger matrix R by R. And we want the size of this extension to be as small as possible. And we want these matrices to commute. Okay. We want all the pairs to commute. And we are looking for the smallest possible R. No, it's not completely obvious by the way that there is always a solution.
Sorry, Pascal. Hi, this is Arkadev.
Yes.
Salut.
Bonjour.
Yeah. Bonjour, bonjour. Just a question. So your R, it's not 2n, right? I'm a bit confused. That AI, BI, the BI is also an n.
It actually, we will see shortly that 2n, the value 2r equals to n plays a special role, but no, it could be any, it could be smaller or bigger than 2n. We just want so yeah, so these BIs, in particular, BI could have more than n columns or fewer. It's not prescribed, so we just want the smallest R.
Okay.
And is it important that the columns or rows are contiguous?
Yeah, that's the way I define the problem. Yes. So you put AI really in the top left corner, literally like this.
Okay, so you're not allowed to like shuffle the rows or columns, and then okay.
No, AI is here in the top left corner, and then the reason for for this choice is basically that it has a connection to tensor rank, as I will explain. Okay. Okay, so it looks like like a natural matrix problem, and when one can try to prove lower bounds on R, on the smallest possible R, and also to one can try explicit constructions, you know. So let's see what is known on both fronts. So I'll start with lower bounds. And this one goes back to Strassen, 1983. So Strassen showed that R is at least n plus one half of a rank of, so it's for two matrices. Okay, so I have just two matrices, A1 and A2. So here, I just have these two matrices, k is equal to 2. Okay, and there's this lower bound here on the extension size. Okay, so you know it is something that makes sense. In particular, when A1 and A2 commute, you don't need to extend at all. Okay, so R will be equal to n, and the largest possible value that you can get in this way is 3n by 2. Okay. All right. So that's from Strassen's work, and it turns out maybe I will. Yeah. Let me just, before making some historical comments, I will just state the theorem that Strassen proved using this lemma. So Strassen, again in the same paper, used it to prove a lower bound on tensor rank. So now you can see that there is indeed, as I promised, a connection to tensor rank. So he actually worked with ordinary tensors, not symmetric tensors, and his result is for a tensor with 3 slices. Let's call them A1, A2, A3. So Strassen proved that the rank of T is lower bounded by n plus 1/2 of the rank of some matrix, which is, it looks a lot like this one here. So it's A2, A1 inverse, A3 minus A3, A1 inverse, A2. Okay. So again, you cannot go beyond 3n by 2 using this theorem, and he actually showed that this is also a lower bound on the border rank of T, actually, but never mind. We are not going to talk about border rank here. So that
sorry,
was,
Pascal, to interrupt
yes?
you once more. So
Sure.
what is the relationship between this theorem of Strassen and the previous problem?
Okay. So the relation is that this theorem uses this lemma here, and this lemma, it gives you a lower bound on the extension size. So the R here is the size of the smallest commuting extension.
Sorry, I didn't understand. So the lemma tells you an answer to a lower bound for the problem that you mentioned.
Yes,
but
yes.
how is that lemma used in the theorem of Strassen?
I haven't explained that.
Okay.
Actually,
But it is used. It is used, is it?
Yes, the theorem uses this lemma. And actually, I'm not going to use it to explain this now because today I'll talk about symmetric tensors and I'll explain more or less everything from scratch. But I won't have the time to present the proof of this theorem here today. But I just say that it uses this lemma, and in fact, the proof of this lemma here it's an important part of the proof, but it's relatively easy. I could show you the proof later on if I have time. The proof of the lemma, it's really two-line calculation almost. You just literally write down this equality between these two matrices, and you get this fairly directly. Now,
no, I was more interested in how that lemma comes into the proof of theorem in the theorem.
Yeah, so I'm not going to explain this, but what I'm going to explain is that how similar lower bounds can give lower bounds for symmetric tensor decompositions. Okay, so that I will explain.
Okay, thanks.
This is actually the newish result that I have. It's how these things work for real symmetric tensors. All right. So this is so for and I should say right away that in the literature, this is the one and only lower bound result that I could find on the size of commuting extensions. And one actually I should mention this term commuting extensions. It's a quite natural name, but where does it come from? It comes from this paper here that was pointed out to me by Guillaume Aubrin. So this, it's a paper from about 2004 on archive, published 1 year later. And as you can see, perhaps it's a paper from the numerical analysis literature. These guys are trying to cook formulas for approximating integrals, multivariate integrals, and it turns out to be useful in quantum physics. You see, two of these authors they are from a chemical physics department, so this is somehow related also to quantum stuff. So these guys, they rediscovered this lemma of Strassen, but they don't cite Strassen, they don't cite any of the algebraic complexity literature, or actually any of the tensor literature at all. They just rediscovered this thing here and applied it to get some interesting constructions in numerical analysis. Okay, so what do I want to explain next? Yes, so constructions. Let's try. So we have this lower bound here, and as I said, that's the only one I know in the literature about the size of commuting extensions. And I can already give you the take-home message, and the message is that we need more bounds like this. we need more. Okay. And you can try several variations. You can try real matrices. You can try real symmetric matrices. We need more bounds like this. Okay. All right. So let's now try to construct commuting extensions. So we are going to give constructions of commuting extensions to see maybe if this is far from from the truth. Let's look at a couple of constructions. So here's one very general way of doing it. Okay, so this construction is due to Yeohan's rhythm, and as you can see, it shows that R can always be upper bounded by 2n. You know, it's a 2n by 2n matrix, this xi here, and the reason that they commute is simply that all the products are 0. Okay. All right. But you see, these matrices are very highly non-symmetric. But we would like to have symmetric matrices because we have, remember, we have series of symmetric tensors. So let's try something else. So here's a construction now that works just for 2 matrices. And for x2, you just permute a1 and a2. You can make the product and check that x1 and x2 commute. And notice that these matrices are going to be symmetric if a1 and a2 are symmetric. So we do have a construction for symmetric matrices, but it's only 2 matrices. Okay, it's 2 matrices. And then for more matrices, can we have symmetric constructions? Well, okay, here's an attempt at a more general construction. I think this is the formula. So we are using complex numbers now. Okay, so I is not an index. I is the square root of -1. And you can see that if my matrices AJ, they are symmetric, then XJ also is symmetric, but of course it's not real. So then there seems to be a difficulty with real symmetric matrices in constructing small extensions, and we will see that it's not a coincidence. And again, the reason why these matrices here commute is that again all the pairwise products are 0. Okay. Just like here. So in particular, these matrices, they are all nilpotent matrices. Okay. They are very special. Okay, so so now what about real symmetric matrices? Well, in that case, we have a connection to tensor rank, to symmetric tensor rank. So we will at least understand what the connection is. So let me state the theorem. And that's going to be theorem 1. So let T be a symmetric tensor of order 3 and size n by n by n. So I think the notation is in multilinear algebra is something like this: S3Rn. And assume that the symmetric tensor rank is less than R. Then there exists
Sorry,
another
what was symmetric rank?
It's the symmetric rank,
Yeah.
symmetric tensor rank. So it's a have I defined this already? So it's the number of if I go back to one of my first pages, where is it? It's the number of terms. It's the number of terms that you need to express.
Oh, wearing rank. Okay, so equal to wearing rank. Okay, okay. Thanks.
Yeah, it's the Waring rank. Yeah, it's another name for the Waring rank.
Okay, good.
It's another name for the Waring rank. Exactly. So there exists another S. So yeah, it's not the S of symmetric, it's a tensor. There exists a S, another symmetric tensor, again of order 3. And size R plus N, such that two properties hold, namely the slices of S commute. And the second property is that T is a subtensor of S. You know, it just exactly in the sense that we had for our matrices, like here, for instance, AI was a symmetric of xi in the sense that, you know, it sits in the top left corner, and it's the same thing here now for tensors. So I just mean that the entries are the same when you restrict to indices smaller or equal to n. Okay, so you know you can draw a picture. I have a picture of this somewhere. You can. So you know it looks like this. You know, that's what you imagine, I guess. Okay, so you have this blue big tensor. The big black tensor is S, and it's an extension of T. T is a small tensor, and it literally sits in a corner of S. Okay, that's what the picture looks like. Okay, that's the meaning of a subtensor. All right, so hopefully I will be able to.
So, question. So, when you say slices commute, or I mean, you want all the 3K slices to commute, is it?
All the.
Because a slice can be done in any dimension, right? In one of the 3 dimensions. Are you talking of slices with respect to one
yes,
dimension?
good point. So, yes, you can have, you know, in general, when you have a slice, you know, you could slice it, you know, like vertically or horizontally, or like this, in 3 different ways. But here we have symmetric tensors, so there's only one way, in fact. All these, you get back the same, actually the same slices. So where is this slide? I have it somewhere here. It's number here. Yeah, so this is my definition of slices. It's here. Okay. So you see here, I decided to fix, to define the slices, to fix the value of a third index. But you could also decide to fix the value of the first or second index. So in principle, you would have like 3 n slices, but you don't get new slices because of the symmetry. So for a symmetric tensor, you just have n slices already. Good. Right. So we have this theorem, and so I'll try to explain the proof. But you can see that in principle, you can turn this now into a lower bound method by taking the contrapositive. If you have a lower bound on the extension size, a lower bound on the size of S, then this implies a lower bound on R, on the symmetric rank. Okay. Okay, so we just have to prove now lower bounds on R. And I see that I'm already running out of time, but so let me and as I mentioned, this was in a way the method that was followed by Strassen in the setting of ordinary tensors, not symmetric tensors. Why should why should we expect that this approach could work? What could go wrong if we try this method here of commuting extensions? What could go wrong? Well, first thing, the sad truth is that proving lower bound on lower bound on extension size is on size of commuting extensions is hard. Actually, as I said, I could only find this Strassen lemma in the existing literature, and but maybe some of you will come up with some new ideas. So that's one potential difficulty, and it's a very real difficulty maybe. And the other potential problem is that so you want to put a lower bound on the rank for some tensor T. But perhaps T has high rank. T might have a high rank, but it might have smaller, it might have a small commuting extension. It's a possibility in theory. you know, if you start from a tensor T with higher rank but small commuting extensions, this method is not going to work. Okay, you will not get much out of it. Unfortunately, this cannot happen. Okay, this is not possible. This is impossible. Okay, impossible. So if we manage to find new methods for proving lower bounds on the size of commuting extensions, I can guarantee you that we will have new lower bounds also on tensor rank. And why is that? Why is it that this problem here does not occur? Because there is a kind of converse to theorem 1. There is a converse. And the converse goes as follows. So let's assume that these two conditions from theorem 1 hold. Okay. So, you know, we assume that we have an extension of S. So T is a subtensor of S. The matrices of S commute. Then the symmetric rank of T is at most n plus R. Okay. It's n plus R. So basically, you know, when you put these two theorems together, this shows that the size of the smallest commuting extension is basically, you know, it's basically a characterization of symmetric tensor rank up to this additive term n. So you lose n. So, you know, here we started with a tensor of rank at most R, and here we have as a conclusion rank at most n plus R. So, but up to this term n, we do have a characterization of tensor rank. And, you know, if we want to, you know, ultimately obtain some nonlinear lower bound, nonlinear in n, then, you know, it's not a problem if we lose n here. Okay. So I could also try to explain the proof of this if I have the time. But, you know, let me show you one more theorem. It's written already on some page.
I'm sorry, could you explain what is R here? R is the size of S, or n plus R is the size of S?
Yes, good point. So I mean that n plus R is the size of, it's the size of S. Yes. So, you know, this means that, you know, for instance, if I start from T, and if I have found a commuting extension of size 100, this means that the symmetric rank of T, my starting tensor, is at most 100. It's the size of S.
Thank you.
Good. Yeah. So you see, so you lose a little bit. You lose this additive term n here, but in fact, there is a more precise theorem which gives you an exact characterization. And, you know, I'm not going to try and prove it, but basically on the same methods, you have to work a little bit more. So let me just put it here. So you know, you see it's an if and only if now, and you have the same two conditions. So you must find an extension of S with commuting slices. But now to get an exact characterization, there is a third property, namely any matrix in the subspace spanned by the slices of S should be of rank at most R. Okay, so these slices, the slices here, they are as you can see, they are matrices of size n plus R. So now we restrict to rank R. We want any linear combination of the slices to be of rank at most R. And if you add this third condition here, you get an exact characterization of tensor rank by the size of a certain commuting extension. All right. So now I could try to give some ideas about the proofs of theorem 1 here and theorem 2. So I should point out that, you know, I don't have any new lower bound, unfortunately, at this point, because of this problem 1 here. Proving lower bound on the size of commuting extensions is hard. So you know, the only lower bound that one can get from this method so far is this old Strassen result. But yeah, hopefully we will get new lower bounds if we can overcome that problem here. Okay, so let's try to present this. Is the statement of these two theorems clear? Theorem 1 and this this partial converse, theorem 2. So you see, if we want to prove these two theorems, we need to understand what does it mean for a tensor that the slices commute. Of course, this is all about commuting extensions. So, you know, if we start from a tensor that already has commuting slices, for instance, you know, what does it mean for a tensor? And in fact, it turns out that there is a very simple answer to that question. And this is going to be theorem 4. So let S be a real symmetric tensor as usual. Of size n and order 3. Then the slices commute if and only if S has an orthogonal decomposition. So what does that mean? What is an orthogonal decomposition? Well, again, it's a decomposition as a sum of cubes of tensor cubes. So you this means that you can decompose like this. You have a sum of UI tensor cube, where now these vectors UI are required to be pairwise orthogonal. Okay. This is the meaning of orthogonal decomposition. So in particular, you know, these tensors have a rank at most n. Okay. So you know, just from the statement of this theorem here, you can maybe already see how this is going to imply theorem 2. Okay, because can you see the statement here? So just to recap, so we start from some tensor T. We assume that we have T as a subtensor of S of size n plus r. And then I claim that the symmetric rank is bounded by n plus r. Well, yeah, this follows clearly from theorem 4 because of just of this observation here, basically. So the application to theorem 2 is simply that now we have k less than n plus r. So the size of S is of size n plus r. That's the that's the size of S. So I have switched notations here. N has become n plus r. This may be a little confusing, but anyway, the upshot is that the symmetric rank of S is at most n plus r, and T is a subtensor. But when you take a subtensor, you cannot increase the rank. It's a general fact. We have that T is a subtensor of S. So the symmetric rank of T, you can bound it by the symmetric rank of S, which is, as we saw, which is less than n plus r. Okay, less than n plus r because you're in a space of dimension n plus r, so you cannot have more than n plus r pairwise orthogonal vectors. So that's how you can deduce theorem 2 from theorem 4, and now I see that I'm out of time, but you can also deduce theorem 1 from theorem 4 with a little bit more work, and basically, you know, I don't have the time to explain the proof, but it's going to be based on the fact that, you know, real symmetric matrices are diagonalizable in an orthogonal basis or in an orthonormal basis. So yeah, one last comment I would like to make. Basically, so why in the end, why is the real setting nicer than the complex setting, for instance, or at least, you know, it's at least as interesting. Over C, you have a similar statement, but you must add the condition that the slices are diagonalizable. Okay, over R, they are going to be automatically diagonalizable because they are symmetric matrices, and that's not true over C. And it's very important to take that condition into account because, as we saw at the beginning, if you don't take this diagonalization property into account, then you always have small small extensions. Like for instance, here over C, you have even with symmetric matrices, you always have extensions of size 2n, but you see these matrices are not diagonalizable because they're nilpotent. So, so that's the crucial difference between the real and the complex case. Okay, so I guess I have to stop here now. Any questions?
Are there any questions for Pascal?
I have maybe like a question or comment. For this, regarding lower bounds for the size of this extension, this R. So you mentioned this result of Strassen, and I think this should be kind of related to the notion of non-commutative rank of a tuple of matrices. So, so this result of like a special case would be this result of Strassen. So, I think maybe you can use this notion of non-commutative rank to get lower bounds for this R. Lower bounds are better than 1.5 times n, but maybe closer to 2.
And do you think that more lower bounds have been obtained thanks to this notion of non-commutative rank?
Well, so the various lower bounds for tensors that get well, in principle you can use this notion of, and has been used, this notion of non-commutative rank to get lower bounds for ranks of tensors, or in some cases just like reformulation of results that were already there. And I think but you can do similar things for this to estimate this R. So it's somewhat similar, I think. Yeah.
Okay. Yeah. So yeah, if you have some specific references in mind, you could maybe email me offline.
Sure. Yeah.
I have seen some of these papers, but maybe I've missed something.
Yeah.
Thank you.